This is the Signals and Systems project for built by Ali, Charles, and me, Raphael. The project is based on a low-pass filter. We have an external board connected to an external deck light board, which produces our signal and feeds the RC low-pass filter. We're gonna take a quick read through the code, and as we can see before the actual code, we have a couple of sets. We're setting the x time sample rate base frequency, an array for time, values of frequency, and capacitance. The first part of the code, the first piece of code is a loop. It goes from uses a counter for index accessing and as a frequency multiplier, because we're testing 9 different frequencies, and these frequencies increase with I, and I goes from 1 to 9. Inside the while loop, first thing, we're creating a signal. We're creating actually a matrix, which each of these rows are one signal. So when we're accessing I equals 1, 2, 3, 4, we're accessing the signals 1, 2, 3, 4, and the second index is for this sample number. The round function takes our cosine and rounds it up to the nearest integer, or round it down, depends. We have the cosine multiplied by 127.5 and added 100.725 to get values from 0 to 255. We're setting the first element of each output to 0, because deck light returns n-1 values. So we set the first value to 0, and then we start writing on a second index of each signal. The deck light function takes signal as parameter, and also the sample rate, and another option we call plot off, which won't allow the default plots, which would mess up with our plot that should come next. At the end, we just increment the counter, and that's it. It runs through this loop 9 times, from 1 until 9, and the 10th time it skips because it's for I less than 10. For the plotting part, we have again another loop. It goes again from 1 to 9, and first we calculate the amplitude of the output by taking the maximum value of the output and the minimum value of the output, make the difference between those two and divide by 2. Then we have the actual amplitude of the output. We're also calculating the amplitude of the input. This piece of code should work to whichever input you're using. Even we already know what input is, we're actually using this for calculation that should come next. We're also calculating the expected output. It's calculated based on an input and in a mathematical formula. It's for further comparison.
Sorry, is that it?
We're gonna compare later.
For comparison reasons.
Yeah, for further comparison reasons. So we have the mathematical formula that has been deducted from the voltage divisor for an RC series circuit. We pretty much calculates the magnitude multiplier that's going to multiply the amplitude input, and it's going to all be plotted together, and you'll be able to see the difference. So the actual plotting comes now. Subplot 3i means a grid with 3 rows, 3 columns, and I we're accessing element by element, and each time we plot a different frequency. So we hold the subplot and we plot like signal against t, which is the input, in red. The output is plotted in black against t again. We're setting labels for x-axis and y-axis, which are voltage and time. Just a second here. Second promise. Okay. Okay. We're also using the title with a number to string function just to make it clear the frequency of each function of each signal we're using, and also legend to make clear each one is the output, each one's the input. It goes through this loop 9 times like the previous loop, and is going to plot one by one. This first part should be enough to see the difference of the output against the frequency. I mean, when you increase the frequency, you get a lower output magnitude, as we'll be able to see in a couple of seconds in the plotting. But we also did another signal, a signal that increased the frequency with time. This signal is not good to comparison to make any calculation, because usually signals take a little time to become stable, because it's not a real sinusoid. It doesn't come from infinity and doesn't go to infinity, so it takes a little while. I would say like from 5 periods to stabilize and
to
stabilize. Sorry, but this is a really good way to see how this works. So we're creating a new signal. First we set the maximum frequency.
This is just an example of the signal that we produced, isn't it?
Yeah.
The demonstration.
The demonstration is also going to be plotted. It's really easy to see. We first set the frequency, the maximum frequency, and then we create an array that goes from 0 until the maximum frequency, and it has SR samples. So we can always count it has SR samples. In this case, SR is 1000, so it has 1000 samples from frequency 0 until frequency 20. And this deck-light this function won't take 2 vectors as parameters. We can multiply them inside a function, so we're using a while that goes from 1 until whatever SR is, and we're pre-calculating all the parameters for the function. So that's it. So we're calculating this var f, which means variable varying frequency. Index I again. Now this time index goes from 1 until whatever SR is, in this case 1000. So we're calculating each frequency and multiplying by the respective time. So we can just use this number inside the deck-light function as a parameter. So you don't have to worry about this problem with the parameters in MATLAB. Once it is done, we can just use this array inside the cosine. The interesting thing here is cosine takes vectors. I mean, if you use a vector as a parameter for the cosine, it's going to return another vector calculated for each of the vector parameters. So we don't have to worry much about it. Just use the vector as a parameter. It's going to return another vector of the same size. And again, we're rounding as the last plotting. It rounds to nearest integers, round up or down depending on the integer. But it gets a really good and close approximation of real cosine. And now we're calculating the output. again, DACLI returns n-1 values, and restoring these values returned by the DACLI function on the output. So when you're calling the plots a couple of lines down, you'll see that we're open square brackets 0 var output close square brackets. We're just compiling a 0 with the actual vector because we need it to be the same size as t. Again, we're doing the plotting of the inputs in red, the plot of the outputs in black, labeling all the axes, putting legends and titles, and that's it. Now we're going to go through the plottings. Well, this is the result of the first plots, actually first loop of plots. As we can see, we have 9 different plots. It goes from 2 to 18 Hertz, and it's easy to see that as we increase the frequency, we get a lower amplitude on the output. And in the title, we have specified the expected output, the output we expect in the previous calculation done by the voltage divisor, only based on the theoretical part of the circuit. And in the legend, in the actual plot, we can see what has been measured, what has been actually measured, and we can compare the difference. Now to figure 2, we have the signal varying frequency with time, and it becomes clear that when we increase the frequency, passing through a low pass filter, we get less amplitude. That's it. Thank you for your attention, and